Something is testing the air through bone. Not breathing it, not smelling it the way you do, reading it. You feel safe in a world with oxygen to spare. It did not have that luxury, and the way it solved that problem still shapes the inside of your own mouth. Around 240 million years before anyone built a microscope to study it, something walked the floodplains of what is now South Africa with a skull built like a hydraulic press, running on an atmosphere that would leave you gasping within minutes. Picture a wolf. Strip away the fur, the warm blood you'd expect, the modern mammalian metabolism, and replace the jaw with something closer to a bolt cutter than a bite. It looked like a predator built for a stable world. It was actually built for a planet still bleeding from the worst extinction event life has ever survived. It's called Cynognathus, dog jaw. And that name, given by 19th century scientists who only had the teeth to go on, turns out to undersell almost everything interesting about it.
What we're going to find is that this animal wasn't a relic from before the catastrophe. It was a direct product of it, a body redesigned piece by piece to function in the wreckage the Permian extinction left behind. Roughly 252 million years ago, the Permian-Triassic extinction event, the Great Dying, eliminated an estimated 90% of all species on Earth. If the same proportion vanished today, you could walk for a year and barely see another vertebrate. Atmospheric oxygen, sitting near 30% before the event, collapsed to levels some researchers estimate as low as 15%, roughly the air at 3,000 meters, roughly 10,000 feet, permanently at sea level. That's the inheritance. Less oxygen, fewer competitors, a reshuffled food web with enormous gaps in it. For Cynognathus, none of that was abstract. It was the air in its own lungs, every single breath. The extinction didn't just kill the world, it rewrote the rules for what came next.
Here's where the biology gets specific. Cynognathus belonged to a group called Cynodonts, and inside that skull, something genuinely new was happening. But how did a low-oxygen world reshape a predator's mouth? In narrative terms, this is a creature racing against its own breath. Biologically, what's happening is more precise than that. Earlier synapsids fed the reptilian way. Grab, puncture, swallow. That works when oxygen is abundant and digestion can afford to be slow. In a post-extinction world running on a fraction of the air, slow digestion was a liability. Cynognathus's skull, around 40 centimeters, roughly 16 inches, solved this with differentiated teeth. Incisors up front for gripping. Canines past 5 centimeters, roughly 2 inches, for puncturing hide. And behind them, postcanine teeth with cusps that sheared meat into fragments before swallowing. It changed what feeding even meant. Smaller fragments mean more surface area for stomach acid, faster nutrient extraction, more energy recovered per breath of thin Triassic air. The jaw wasn't just for killing, it was a metabolic accelerator bolted onto the front of the skull. Inside its skull, the problem was simpler than any of that. Survive the next breath. The teeth were just the answer it found. There's a genuine debate among paleontologists about how far that efficiency went. Some reconstructions, based on jaw muscle attachment points, suggest a bite force exceeding 200 newtons, roughly a 20-kilogram, roughly 44-pound weight dropped from a meter up, concentrated into a single bone-on-bone impact. Other researchers caution the muscle reconstructions remain incomplete, and the true figure could be considerably lower. The truth is still being worked out.
What isn't contested is the cost.
A jaw with this much shearing power demanded a skull rigid enough to survive its own bite without fracturing. Heavier bone, more mass to move, more calories to fuel that movement, in an atmosphere already starved of the oxygen needed to convert food into usable energy. Every adaptation here is a trade. Nothing was free. Its most dangerous feature, though, wasn't the teeth at all. It was something happening in its sinuses, far more subtle and far more consequential for everything that would eventually evolve from animals like it. Researchers studying the nasal cavity of Cynognathus and its relatives have found turbinate bones, thin scrolls of bone that would have supported soft tissue in life, suggestive of an early respiratory upgrade. In low oxygen conditions, extracting maximum value from every lungful of air isn't a luxury. It's survival arithmetic. A more efficient nasal passage, warming and moisturizing air before it reached the lungs, may have allowed a higher metabolic rate than its sluggish Permian ancestors could sustain. Think about what that means for a moment. You are looking, in this unglamorous Triassic predator, at one of the earliest structural hints of the path toward warm-bloodedness. The trait that built every mammal, including the one currently watching this screen. This wasn't a predator that simply ate more efficiently. This was a body beginning to rewrite its own metabolism.
For decades, the common image of the early Triassic was a barren stage with one or two struggling survivors wandering an empty set. That's not what the fossil record shows. Within a few million years of the extinction, a geological eye blink, ecosystems were already reassembling, just with unfamiliar casting. Dicynodonts, tusked plant eaters with no proper teeth otherwise, were rebuilding their numbers faster than predators could stabilize around them. That mismatch creates pressure. Every recovery ecosystem asks the same brutal question: who eats first when everything is still unstable? Cynognathus answered it by sitting near the top, not as the last of something, but as one of the first true apex predators of the recovery.
Pull back far enough, and the scale gets strange fast. Cynognathus fossils turn up not just in South Africa's Karoo Basin, but in Argentina, China, and Antarctica. Then a forested, temperate landscape, holding teeth identical to ones found a hemisphere away. The distribution spans Pangaea, a single connected landmass covering roughly 200 million square kilometers, roughly the size of all 7 modern continents fused into one. These animals had no idea those continents would later tear apart beneath oceans not yet formed. This wasn't a regional curiosity. It was a successful body plan radiating across an entire world in the immediate aftermath of the worst extinction the planet has ever recorded. And it's precisely why Cynognathus became a key index fossil for dating early Triassic rock layers across continents now separated by oceans. Find its teeth in 2 places, and you've proven those 2 places were once joined. But success at this scale invited competition.
Rausuchians, early archosaur relatives, were testing a different answer to the same exam. How do you hunt efficiently when the air itself works against you? Where Cynognathus solved it through jaw mechanics and possibly accelerating metabolism, the archosaur lineage was experimenting with upright limb posture, a cheaper way to move, conserving the very oxygen Cynognathus was straining to extract more value from. 2 different evolutionary answers to the same low-oxygen exam. Only one lineage would still be sitting it 50 million years later.
Cynognathus vanishes from the fossil record by roughly 235 million years ago. A run of perhaps 10 million years, roughly 40 times longer than the entire span of recorded human history. The end wasn't one dramatic event. It was arithmetic, failing slowly. Run the numbers.
an active predator of Cynognathus's likely mass, somewhere between 50 and 90 kilograms, roughly 110 to 200 pounds, with a metabolism trending toward warm-bloodedness, needed substantially more daily caloric intake than the sluggish ectothermic predators it had replaced. That worked while prey biomass was abundant in the recovering ecosystems. It stopped working as the Mid-Triassic climate shifted, increasingly arid conditions spreading across Pangaea's interior, shrinking the dense vegetation the herbivore base depended on.
Fewer plants, fewer Dinosaurs, a shrinking prey base for an animal that needed a high, steady caloric return just to keep its jaw muscles and elevated body temperature running. Researchers estimate territories may have needed to expand several-fold to sustain the same population density. At some unrecorded threshold, the energy equation stopped balancing. More territory required more energy to patrol than the territory itself could supply.
For Cynognathus, there was no warning system for this. Just smaller meals, wider ranges, and a deficit that compounded with every season. Imagine the climate had stabilized instead of drying. A surviving Cynodont lineage already running efficient jaws and an accelerating metabolism continued uninterrupted for another 30 million years. The mammalian body plan, warm blood, differentiated teeth, efficient respiration, might have arrived tens of millions of years earlier. The small, shrew-like mammals that eventually outlasted the dinosaurs might never have needed to stay small at all. And here is what that means for you. The differentiated teeth in your own mouth, incisors, canines, molars, each shaped for a different mechanical job, are a direct architectural descendant of the jaw innovation this animal helped pioneer. Every time you bite into something and chew it before swallowing, you're running a solution this Triassic predator helped engineer 240 million years ago. Evolution didn't abandon Cynognathus's design. It just kept building on it. Something is still testing the air through bone. Not the way it did then. Not reading oxygen scarcity in every breath. You don't feel the difference. But the body doing the reading is the same one it left behind. It walked a recovering world on borrowed air, with a jaw built to survive a catastrophe it didn't cause. It lost its own arithmetic in the end. It did not vanish. It was rewritten, and the rewrite is still not finished.